Materials are often placed in service at elevated temperatures and exposed to static mechanical stress. For example, turbine rotors in jet engines and steam generators that experience centrifuge stress and high pressure steam lines. These are the examples of materials that will experience high temperature at a static mechanical stress. The materials that experience static mechanical stress under high temperature will undergo a time-dependent increase in length. That means the length of the materials will get longer as the time increase. And this can be dangerous if we use it over time and time. The strain or the elongation of the material getting longer, is measured as a function of time. Okay, so this is the graph that represents the creep process, the process of creep across time. So x-axis is time and y-axis is the strain, okay, or the elongation. Okay. And if you can see from this graph, there are actually 3 different stages of creep, okay, before the material getting or become rupture or fracture. Okay, the first is a primary creep. Okay. This is happen when we apply the load, okay, on the material. There is an instant or immediate deformation. Okay, this is mostly elastic. Okay, this region is mostly elastic, where deformation is immediate or instantaneous. Okay, when we apply the load. And then we have secondary creep. Okay. For this secondary creep, or sometimes also called as steady state creep, where the rate is constant. The rate here means the change in creep strain value divided with the change in time. We will get a linear curve, some sort of a linear curve, linear shape of the graph. Okay, so this is often the stage of creep that is the longest duration. So that's why you can see, as compared to the primary and the tertiary stage of creep, so the secondary stage is the longer period of time. And finally, the tertiary creep, okay, where there is an acceleration of the rate and ultimate failure. Okay, it will experience failure. Okay, so this failure is frequently called as rupture, and this results from the microstructural or metallurgical changes. Okay, for example, there is a grain boundary. There is separation between grain boundary or the formation of internal cracks or micro cracks, cavities, or voids. Okay. Or it can be also a tensile load, okay, that form a neck. Okay, at some point, and making the material become rupture. Okay, both temperature and stress level or magnitude of stress will influence the creep characteristic or the shape of this creep versus time, creep strain versus time graph. Okay, but both higher stress or higher temperature will reduce the rupture time. You can see we have one curve here with high temperature, or can be also high stress, as compared to another curve here represents the low temperature or low stress applied. Okay, the rupture time for high temperature is much faster to happen. Okay, the rupture is faster to occur as compared to the material that is exposed to the low temperature or low stress. We can minimize the creep effect on the materials by using high melting temperature materials, high elastic modulus material that has high elastic modulus, or material that has high melting temperature, or material with a large grain size. Okay, large grain size meaning the particles of the materials are large. So where if we use large grain size, it will inhibits the grain boundary sliding. Okay, the grain between grain will not experiencing sliding. Okay, these are the materials that able to withstand with creep. Can be stainless steel, okay, refractory metals, or super alloys. So these materials are normally used for high temperature application with high stress level. For example, in turbines, okay, turbines in jet engines, hypersonic airplanes, nuclear reactor, and so on.